Can I access the link from another device easily?
Yes, sir.
What is the name of the thing? Okay, it is Zoom. No, I'm increasingly finding out that I'm not that tech savvy.
It's okay, sir. We know these are our senior web admin. He will always there to help you.
Okay, very good. Okay, let's see here.
Thanks, Vinod.
Okay, thank you.
Thank you so much.
Thank you, sir.
Can I use a pointer? Is it possible in the when I use this? My pointer doesn't work here in the screen. Oh, here it is. Let's see. It works. Pointer. Okay. Okay, it looks like you've asked for some access that I've given it to you. Okay. It's without the pointer.
Vinod,
Yes, Papaya.
so I don't have the, that host setting, right? You are the,
Yeah,
I'm
yeah,
also,
yeah.
I'm also not co-host. I'm showing me as a just, participant. So make me co-host.
Already I made that, Papaya. You are in co-host right now.
But Rohan is asking me to make him co-host, but it's not showing. I'm not able to make him
Yeah,
co-host.
okay. I will make it a co-host.
Okay. So sir, like now we
Yes.
have 20 participants, so we can start the session. Or you
Okay.
want to wait for
You,
2-3
I'll
minutes?
leave it. I'll leave it to Gopal.
I think we can start, and if they join in, they can just they'll be joining in. So we need not just wait for everybody to join. They'll be joining in. Okay.
I would request all participants that have joined the session to mute themselves. So please, Papia, introduce our speaker and then
Yeah,
we
yeah,
can move forward.
I will do that. Thanks everyone for joining the session. I'm requesting Mr. Gopal, our Chennai chair, to introduce the speaker. Thank
Yeah.
you, Gopal. It's over to you.
Yeah. Thank you, everybody, for coming on board for this session. Thanks to Professor Ramnath also for agreeing to just host this session for the alumni. And just as a brief history of these talks are called as Guru Talks, and they are organized by the IIT Madras Alumni Association. Okay, so this is in the series of the Guru Talk, where we invite esteemed professors throughout the world to just share their knowledge with the alumni. Okay, so as an introduction of Professor Ramnath Ganapati, he is the John Todd Horton Professor of Department of Material Science and Engineering, Rensselaer Polytechnic Institute, Troy. He is a Vice Guest Professor, Wallenberg Initiative on Material Science for Sustainability, Angstrom Laboratory, Chemistry Department, Uppsala University, Sweden. He is a Visiting Professor, Center for Indian Knowledge Systems, for mental health applications, IIT Mandi, Himachal Pradesh. So Professor Ramnath today he'll share key highlights from his inspiring journey as a researcher in the field of nanomaterials discovery and interfacial engineering with applications in energy and electronics. Through compelling examples, he will illustrate how a combination of skill, attitude, experiences, and creativity can foster serendipitous moments and second chances, often leading to scientific breakthroughs and the crossing of new frontiers. He'll also reflect on his personal engagement with music and wellness practices and how his efforts in promoting Indic heritage values and spoken Sanskritam have led him to explore Indian knowledge systems where art, science, and practice converge in meaningful meaningful ways. Professor Ramnath will conclude by offering his perspectives on the transformative potential of integrated exploration across art and science. He will highlight how such an approach not only fuels intellectual curiosity but also nurtures personal growth and collective well-being. So all his friends tell me that Professor Ramnath is a very versatile singer. So at the end of the session, after the audience question is over, I'll just request him to sing for about 2 or 3 minutes, any genre of his choice. So that he must agree to. So Ramnath, the floor is yours. Please start the session. Thank you.
Thank you very much, Gopal. It's a pleasure to actually be talking to our distinguished alumni. I must say that this is one of the talks that I had after I wrote the abstract. I really thought about what I need to say because everybody in this audience is very distinguished, being from IIT Madras, and I'm sure they are from various fields. And I was just wondering, what is it that I could share that they might not know? Well, then I reframed the question to myself, saying that I'll rather share what I think I want to share and what I think I know a little bit about and what I think I have learned over the last about 30 years or 35 years since I have left IIT Madras. So I'll first talk about discovery and design of nanomaterials. What are the key things that may work in this area, at least from my perspective? And I will obviously draw mainly from my research. I'll pick some examples, and then I will talk about my journey as we go along just a little bit. And then I'll talk about Indian knowledge systems towards the end. So are you all able to see my screen?
Yes.
Okay, very good. Thank you. So since it is Guru Talks, I thought I should start with Guru Vandana. Sada Shiva Samarambham Shankaracharya Madhyamam Asmadacharya Paryantam Vande Guru Paramparam. So I have been inspired by so many people, so many gurus, and a few of the key ones I have kind of put a collage here. You may or may not recognize many people here. First, I will talk about what I really learned from the central figure here. This is Professor Joe Green. And much of my research in terms of what I learned really was under his mentorship. He was not even my advisor, but I, during my PhD, worked with 5-6 professors. I was very gregarious, and he was my de facto advisor rather than de jure. And so what I'm going to share is really all the things that I built upon that I learned from him. Then we will talk a little bit about what I learned from the others in the context of Indian knowledge systems and how that is integrating with my research interests presently. So, material science, what is new really? Well, civilizations are named after materials. You have Stone Age, you have Iron Age, you have Copper Age, you have Bronze Age. And now probably we're in the Silicon Age or Aluminum Age, depending upon if you talk to somebody in the Silicon Valley or in the automobile industry. Now, our forefathers were actually quite brilliant in discovering materials and using them for various different applications. Now, the paradigm has shifted. We can actually tailor make materials that we want, in terms of what kind of properties that we would like to have. We can have a combination of, let's say, optical transparency, electrical conductivity, lightweight and toughness and what have you. And we can design them at the atomistic scale. And the main reason for this is we have access to a very wide variety of spectroscopy and microscopy tools to be able to image and get evidence about how atoms are arranged, where they are, what kind of atoms are arranged, and we can use that as a feedback. Does it make us smarter? Not really. Our ancestors actually was much smarter because they designed materials without even knowing the knowledge that we have now through spectroscopy and microscopy. For example, if you look at the flexible but very sharp sword made of Damascus steel that actually was made in India, and India was very adept in materials technologies. Okay, so here is a collage that shows you a whole bunch of things. The top left shows you an array of carbon nanotubes that are organized. I'll show you that in a minute again. And they have decorated nanoparticles on nanotubes, which I will show you also in a couple of minutes. You can see nanoparticle assemblies, branch structures, you have heterostructures, and we can make bulk materials with that. I will talk about that very briefly. And then I'll focus on talking about how we can put a molecular layer, a single molecular layer between two materials at a thin film interface. And we can dramatically change properties, and we can do this at will. And I will talk about that aspect a little bit more because that was pioneered in my lab about 25 years ago. And this came just through courageous daydreaming and just trying things out and not believing the textbook things of, oh, that will not work, this will not work. So a very important aspect of scientific discovery and research, as most of my colleagues here would know, is about trying things and trying to look beyond what theories, established theories tell you. I'd like to briefly acknowledge all my students and postdocs who have contributed to the work and collaborators worldwide. I must say I've learned a lot from collaborators in Sweden, in Germany, in Singapore, in Australia, in India. I have several collaborations at different points with different IITs and NCL and NPL, and now with IIT Mandi and IISc. I am very grateful for funding from multiple agencies which are listed over here. Now, when I was doing my PhD, I was actually looking at a very simple problem. There was this metal layer, tungsten, that was just delaminating, and you can see the volcanoes that are forming. And this was very relevant to microelectronics devices. People did not know why it was delaminating. Every time that such a delamination happened, it was $50,000. So when I had actually learned all my skills of microscopy and spectroscopy, working with 3-4 different people, running here and there, like a kid in a candy store at the University of Illinois at Urbana-Champaign, my advisor came and said, hey, this company wants you to figure out why this is happening. And that became my PhD thesis. So after preparation for nearly about 3.5 years, learning many skills and publishing many papers, I did my PhD thesis really in about 6 to 7 months. So what we found really was that the titanium nitride layer, which is on the left side, which is written TIN over here, that is porous, and the tungsten hexafluoride was going through it, and that caused reactions, which gave rise to essentially TIF3 formation, TIF4 formation, which broke up these layers. I'm showing some schematics here. These are all drawings that I had made at that time. And every single aspect of it was based upon microscopy and spectroscopy. I've shown 2 images on the right-hand side, which is catching the tungsten diffusing through the porous layer in the act. This was quite a cool image at that time. You can see the bright regions marked tungsten are actually, they have the same orientation as the porosity shown schematically on the left. And then you had TIF4 formation, which is stressing. So what did I do in my PhD? I had a lot of fun learning many techniques, meeting many people, talking to many people, and all of that stuff. And this, I really found my foundation for being actually quite fearless in exploring different problems, because I was strongly founded in my fundamentals. I must say that at IIT, though, I was not a very good student, in the sense that I used to go to class only occasionally. I thought, sleep and bridge and talking with friends and doing other things like, Mardi Gras, internal publicity was quite exciting. But once I came to the US, I realized that if only I had spent even at least 10% more, I probably would have done a little bit better. And that I kind of did at the University of Illinois. Now, here is one of the first things that I did when I came to RPI. And you can see this can actually win. In fact, this has won many art, science and art, or art and science kind of competitions. It has won many prizes. What you're seeing here is a flowery architecture and oriented architecture of bunches of carbon nanotubes. Now, carbon nanotube, actually, it's like a black little powder that is shown on the left side top. And when my colleague came and said, oh, this would be good to use in microelectronics, I said, not in a million years, unless you do something to orient it, in a highly precise way, in a way that you want to orient it. And we figured out a way of chemical vapor deposition, which is completely a bulk process, but the selectivity on silica as opposed to silicon gives you this orientation. You can make these brilliant architectures. So when I came to RPI, I met with many people who were actually doing things, making things, but were not necessarily as rigorous as I was as a graduate student. And I very quickly learned that to be able to make new discoveries, I need to blend high level of, what do I say, rigor, at the same time also creativity. Sometimes these are opposite of each other. We need to find the right balance so that new ideas are driven by creativity, but proving them is driven by rigor. So let me give you one more example. This is on thermoelectric nanomaterials. We worked on this area for nearly 15 years. So thermoelectric materials can convert a heat gradient to electricity and an electric gradient to heat. So it can be used, or it can be used for also creating cold surfaces. So it can be used for solid state refrigeration. So one of the problems in this is to be able to get high efficiency, you need to get high figure of merit, which means that is ZT, that's given by ZT over here. And the ZT depends on three properties: alpha, sigma, and kappa. Before, there's not some kind of a Greek fraternity. Alpha here is electrical conductivity. Sorry, alpha is Seebeck coefficient, sigma is electrical conductivity, and kappa is thermal conductivity. These three are unfavorably linked in nature in most materials. So when we thought about this, we found that, okay, kappa, basically you can make it as small as you want by nanostructuring, which is good. And alpha, it matters more because there's an alpha squared. So even though there are variations of these in three different directions, if we focus on alpha, we can get somewhere. And what we did, I'm just going to show you one example here for the case of antimony telluride. In our case of sulfur doping, which we found serendipitously, we had no idea sulfur was getting into this material. Okay, we were just using sulfur terminated molecule to make these materials. And then when we characterized this, we found that sulfur is getting into it, and we found it's doing magic. So ideal material, tellurium sits in tellurium sites, antimony sits in antimony sites. But in real life, thankfully, there are defects, so there can be anti-site occupancy. Now, anti-site occupancy is bad because it can create more charge carriers and decrease the alpha. When you put the sulfur, it suppresses it. So this is what we found by a whole bunch of spectroscopies, microscopies. I've shown one key figure on the right side, which we did by synchrotron spectroscopy, X-ray photoelectron spectroscopy. And this essentially gives us amazing figure of merit. Okay, so that was one aspect of many things where we could improve properties. And here is kappa decrease. We know Wiedemann-Franz law, thermal conductivity, electrical conductivity, they're correlated. Now, when you decrease the grain size, you're able to, on the pore size, you're able to get low kappa. So this is actually well known. What we did then was we did this for a whole lot of materials where we were able to shape and size the nanostructures. In this particular case, we were able to make nanoplatelets. And we were able to do this by a scalable microwave process where chemistry does the job for you. So we just put the right reagents, the right surfactants, and then microwave it. You just cook it, just like heating or cooking something in a microwave. And we get these platelets decorated by these molecules. And then what we did was we took these nanoplatelets and made into bulk material where the nanostructuring is still retained. And lo and behold, what we found was quite a big breakthrough. We found that the figure of merit actually goes from around 0.3 to 1.1. I mean, this kind of large change, that too by a scalable process, made a big splash. There's some, references. You can Google this. You can find out, many stories on this. And this works for many materials. So a combination of nanostructuring and doping and microwaving was kind of a beautiful recipe that could be an industrial solution. So we founded a company called Therma Aura Inc. And you can see the team on the left side. And the guy in the center was my graduate student, Ritik Mehta, was brilliant. He also had very good business acumen. So we actually scaled this up to ton scale manufacturing, got several patents and trade secrets and so on. But we found that this is an oligopoly in this industry, and we had to actually go to devices, etc., to be able to make money. And so we kind of transitioned this to another company and looking for opportunities for taking this further. That's what the new company is doing. I was also, during this time, I was director of a Center for Future Energy Systems, worked with lots of different companies, enabling industry university partnerships. So just wanted to quickly show you this to show that aspect of my journey. Now, let's talk about this molecular nanoglue. This was another big breakthrough that happened in 2007, really. But we had prepared for it, when I had come to RPI from Illinois. Basically, the idea was this. When I have two very thin layers of materials, I don't want them to mix up, and I want them to adhere well. And the solution for this usually is put something in between, another material, which is not a good idea for microelectronics. So we said, how do we make a near zero thickness solution, come up with a solution? And we just hypothesized. I just thought, how about putting a bunch of molecules that can bind? This is a wild idea, which I must confess, even I did not believe when I thought about it, but then we tried it. We tried it for about 6 months, a year, and we did a whole bunch of experiments, one of which I'll show you over here. Here is leakage current on the y-axis, and all of you can read graphs, and on the x-axis is time. So we have a capacitor that measures the copper diffusion into silica by the leakage current. So high leakage current without anything, it says control. But if I put a molecular layer, what happens is with amine terminated SAM, that leakage current driven breakdown is actually postponed. If I put carboxyl group, it is further postponed. And all this is blocking copper diffusion, okay? Now, this molecular layer actually is blocking copper diffusion. And we had to do this about 50, 70 times for me to really believe it, even though I had hypothesized it originally. And this really opened up floodgates for many, many possibilities, which I'll share with you in the next few minutes. Now, not only does this block diffusion, it also actually enables adhesion, because the strong hooks on the top and the bottom with the copper and silica in this case gives you strong bonding, which I was able to envision, but we actually measured it in a macroscopic experiment with 4-point bending that is shown on the top right. But here, just look at this graph. The red curve shows that it's 3 times, the plateau is 3 times higher than the plateau in the blue curve. So you're increasing the adhesion energy, the fracture energy, by a factor of 3. And, like at some temperatures, if we increase to high temperatures, the molecular layer is not even the weakest interface. The epoxy that's holding, to a dummy sample for experiments is actually breaking. So the results that we found were like just mind-boggling in terms of never expected, even when we hypothesized it. So I just want to mention here, of course, we learned about the mechanism, what is happening, what this, which I will not bother you with too much because it's technical detail. But I just want to comment here about, suppose we had thought, oh, that would not work. Single layer of molecules, no, that's not going to adhere or block any, diffusion when even much thicker layers are failing. So if we had gone by, what was already known, if we had not challenged this, all these new possibilities would not have been possible. So really what happens is shown in the schematic. Here, on the right side, just look at the right side, this SiO-Si bonds that form, are water resistant when you heat it to high enough temperatures, so you actually get good adhesion, upon heating. We applied this nano glue for many applications where, Teflon-like materials like carbosilane and others, they don't stick, but these are needed for low dielectric constant layers in microelectronics. But we figured out that by putting one layer of hooks, we can have the material hooked, and it actually works quite nicely. Many times I get a phone call saying, "Can we have some nano glue?" I say, "No, it is not a material, it's a concept, so it can actually work for any material system." Then we went on further. Suppose I put a soft material between two hard materials. Normally, what you would think is that the adhesion would actually go down, but in this case, the adhesion is going up, and also your thermal conductivity you would think will go down, because soft materials usually conduct heat much less efficiently than inorganic materials. But we said we have strong bonding and we have carbon-carbon bonding, and these are single layers, so we should get an increase in thermal conductivity, and that is indeed what we found. You see this on the graph on the right side. Thermal conductance actually scales us with interfacial toughness. And this again was a fundamental breakthrough that was not known, so got us another Nature paper. So we can also use these to enhance electrical conductivity, and this again was totally non-intuitive. These molecules are not conducting, okay, and you put them at the interface, you would imagine that the conductivity will go down, let's say between copper and bismuth telluride. It's a metal semiconductor interface, okay? But when you put the molecules, the conductivity actually did go up. And I mean only the contact conductivity, which we measured by special techniques like oxygen stack. When we looked spectroscopically at the interface, we find that on the right top, you can see the red curve has lower peaks than the black curves. And that is because the molecular layer is reducing the oxide. It is scavenging the oxide away, enabling good conduction. So mechanisms are, several. We just need to kind of think about those possibilities before we rule new ideas out. Let me give you one last example before I switch gears. So the same idea here, using these molecular layers at the interface, and you see a polymer on top and a ceramic at the bottom on the left figure. Suppose we load cycle it. So we are doing dynamic loading. What we find is that, now let us look at the bottom right. You can see when there is a molecular layer, which is MPTMS, you are able to get a peak in the fracture energy at certain frequencies. And that peak is absent in the blue curve, which has no molecular layer. Okay. And this is very significant because, normally when you have a weak interface and you put this molecular layer, yeah, you will enhance the adhesion, all right. But how come it is actually giving you enhancement only at certain frequencies? When we looked at this, well, first thing, we always do when we find a new thing is try to make the effect go away. So we change the water content, and you see that the peak, you see on the top left, goes away. It becomes flat immediately in the middle. So water is important. So what is the molecular layer doing? It is actually strengthening the interface, and strengthening the interface is an important condition. Second thing that we did was, instead of using a hard polymer, instead of using a soft polymer, bottom left, please, you see a soft polymer, you get a peak. Hard polymer, you don't get a peak. So something is happening in the polymer. Very right graph, you can see I can also control the peak frequency. I can move it around if I change the temperature, which changes the polymer properties. So essentially what is happening is, and that is shown in the top left graph here, the polymer is getting deformed when there is interface strengthening by the single layer. When there's strong bonding, the load transfer can happen to the adjacent layer and energy can get dissipated there, which will give you an increase in fracture energy. All right, so we got very excited with all this, and we said, if a single interface we can increase so many properties, and there are several others that I haven't talked to you about, but this, you get the picture. We said, how about we build a multi-layer where we have multiple such interfaces, and now we can get superposition effects at the interfaces and get completely emergent properties. So we did some simulations of these, with a colleague, Professor Kablinski, who's in my department. And we found that you get these mechanical band gaps. You get viscoelastic band gaps, and this is a completely new concept. You all know electronic band gaps, photonic band gaps, phononic band gaps. So in the mechanical regime also, you can actually find this. So we then grew these layers, and you can see on the top left, you can see actually multiple layers, and each of these layers is only 2 to 3 nanometers, and there are 20 interfaces, all changed by modified by these molecules, PBPP and PDDP, and we were able to optimize that, and this was a project in itself. But I want to just tell you what we are doing now. When we explore the gigahertz and sub-terahertz properties of these materials by pump probe spectroscopy, we find something very exciting. Now, normally, when you put in a pulse, let's say of a mechanical wave, you would imagine it'll get damped because there are multiple interfaces which has these molecular layers. But then, when we put these multiple layers, we find, as you see in the graph on the right side, at certain frequencies it damps, which is shown by blue. At certain other frequencies, the signal is actually amplified. So that is why I've written this as photoacoustic or optoacoustic damplification. I like to play with words. I was spectator editor at IIT, and I've carried that learning to creating new words, which actually comes from, I think, I would say deep appreciation for Sanskritam and Tamil, but that is yet another story. I'll just hit upon that in a couple of minutes. So damplification tells you it is damping and amplification, which is frequency dependent, and it captures both. And this is a new phenomenon which actually provides the evidence for the interfacial band gaps, because you need to have damping as well as amplification both together for such band gaps to exist. So we're just writing this up. The last thing that I'm going to share with you is these molecular layers we hypothesized can actually wet metal layers. That is, if I put a metal layer on top of this molecular layer, I should be able to form them much thinner, to get a continuous layer than if the molecular layers were not there. And we indeed hypothesized, and we have found the evidence for this. You can see here on the bottom left graph, the red data points basically, follow islanding. So, there is island growth of these metals that is shown by atomic force microscopy on the top over here on the right, which shows the roughness is around 0.87 nanometer. But when I put the molecular layer, APTMS, we actually get a different trajectory, which shows more like layer by layer growth, which is actually giving us much smoother films. This is of critical importance for microelectronics and nanoelectronics device technologies. So this is the kind of things that we are playing with. The very last thing, this is like totally new. We said these molecules at the interface, they can bond, they can also debond. So how about we use the tendency for the molecules, or the ability for of the molecules to bond and debond, to be able to relieve stresses at the interfaces, because thermal expansion mismatches lead to all kinds of failures in all kinds of systems. It's very ubiquitous. So if you put this molecular layer, it not only strengthens, but then since it is also has a flexibility, it can, stretch, and it can change its conformation, and it can also break bonds and form bonds in a sequential manner without affecting adhesion. And the simulation actually shows here the out of plane stresses. You can see with I see the red curve going up and down. This for 100% coverage, there is actually bond breaking, bond reformation, bond breaking, bond reformation. So there is actually stress relief happening, but there's local stresses that are going up and down. But if I have a 50% coverage, which means I'm creating a defective molecular layer, let's say with 50% coverage, now my adhesion actually is decreased. All right, which means it's basically that is determined by the number of bonds that I have. But then I'm also relieving all the stresses that I see over here. There's no stresses that are seen at the interface. So we need to validate this experimentally, and that's what we'll work on. Okay, the last part of my presentation coming back to gurus who have inspired me, I must say that science and research and engineering is actually one part of a potpourri of a variety of things that I explore. And much of it was actually, I think, seeded during very early years of my life, and which I was able to build upon and continue and nurture during my IIT days. In fact, IIT days were very, very lovely because of engagement with extracurricular activities, dumb charades, bridge, music, light music, all kinds of things. Um, and once I came to the US, that continued actually throughout. I was in Cincinnati, I was in Illinois, I was involved in not only in music, but also in rediscovering and relearning Indian history from the original sources to learn, for example, that, Aryan invasion theory is not true, for example. And so many things that we had learned during our school days are not quite right. And how come there is, our rich tradition, our rich heritage, which I had been exposed to because I come from a very traditional family that is very open, that I was able to kind of inquire that or ask those kind of questions. And that's what led to diverse interests in looking at very many things. Couple of examples of which I will share with you. Now, when I say gurus in the left, actually many of them are manasika gurus. Some of them actually have met in real life. Dr. Balamurali Krishna, Sadhguru Maharaj Charan Singh ji, Pujya Swami ji, Pujya Gurudev Chinmayananda, all those I had the privilege of interacting with either during childhood or during my adulthood as well. And of course, my interest in music and chants and also teaching kind of was fueled by all this, because when I was a kid, even as I was a toddler, I used to play, the game that I used to play was teach other kids Indian heritage. Like chants, bhajans, if my parents' friends came, they would become kids and to take lessons from me. Now I continue my music journey, which I'll share with you in a couple of minutes, where I've learned from many legends like T.V. Gopalakrishnan, from Balamurali Krishna, and currently I learn with Chitravina Ravikiran ji. And then, of course, Sadhguru has been a huge inspiration in many, many ways, which I will not describe today. But it is also showing, it's manifesting in different aspects of my approach to research, approach to life, and some of which and of course, to approach to the well-being and reclamation of Indian leadership in the world stage, across the board as a Vishwaguru. And this is not a political statement. This is more like a civilizational aspiration, and that is realizable, at least from what I have learned and what I know. So here is something that I did for 20 years. When I came to Albany, I taught Indian heritage. I created my own curriculum with Chenmaya Mission combined with Ashavidya Gurukulam, with Ramakrishna Paramahamsa tradition, and like that is Ramakrishna Mission's traditions. I combined all those and I created a curriculum. For 20 years, I taught this class. I was kind of the main teacher who created the curriculum, and also trained teachers to basically expose Indian origin kids in the United States to their rich culture, so that they can feel confident, about their culture and identity, and also be able to learn, how to integrate well with the society anywhere, around the world. That led to, actually, during all of this, there's been a lot of storytelling, there's chanting, and so on. But that opened up the doors to my exploration in Sanskritam. I now teach spoken Sanskritam. I've been doing this for the last 10 years. And first I was doing it to kids, and now I'm doing it mostly to the elder kids who have kids, because often parents tend to outsource learning. But I think we all should be students first before we teach. So there's a lot of activities in the Sanskritam area. For those of you who are, computer scientists, and Ashtadhyayi is an amazing book. And this Maheshwara Sutrani, which are listed over here by Panini, is amazing, like code for what do I say? It's a cryptic code which is used in programming, in organizing how Sanskritam is organized, and also to set up these rules in very, very pithy and concise fashion that is self-consistent. I'm still learning some of these. Okay, so let's see here. So this is I put Sadhguru here, and I would say the interest in. Are you still able to hear me? Are you all able to hear me?
Yes, yes, we can hear you, sir.
Okay, very good. So, I was brought up in Mylapore and in Bangalore, where these temples, was like dime a dozen. This is the Kapali temple on the top left that you see. And of course, the one on the right side is the Chidambaram temple. And these are very rich architecture. But I had absolutely no clue about the grandeur of these things until I came to the United States. And the iron pillar, I had even seen that many times before that fence that is put nowadays so that, to protect it from people's touch. This is from Delhi. This is from our civilization where our ancestors had devised a way to keep iron from rusting. Okay. And that is by adding some inorganic materials. In fact, these were intriguing me. How come these are, like such huge and beautiful architecture is connected with the divine, and what is it that what is there in the Vigraha? What are the materials that are used for it? In fact, there's a thing known as Ashtabandhana, below which is the Maheshwara Sutras that are written usually, and these hold the Vigraha for at least 12 years. And what is it? When is it that actually the stone becomes a consecrated Vigraha? These are the questions that were buzzing in my mind, actually, generally over the periods of, long period, rather than dismissing that this is just a stone, is just a symbol, etc. Because when we go to a temple, it's a subjective experience that we actually see. We actually feel sense of peace. We see the arati, we see lovely, calming of the mind and so on. Now, when I came in contact with Sadhguru and his, like processes, which I learned and which I also had the good fortune of practicing, I visited Dhyanalinga and I was really blown away, because for those of you who have visited, you probably know. For those of you who don't, I invite you to do this. And this is by no means a unique thing. This is just a very highly amplified form of what is there in every single temple. And to the right, what you see over here is actually Linga Bhairavi Yantra. Now, why is the material scientist talking about this? Because I was fascinated. A yantra is always made either with copper or gold or silver, usually copper or an alloy. And mercury is always playing an important role here. So Dhyanalinga has mercury inside it. Linga Bhairavi, has the mercury inside it. Now, all these materials have very special electronic structures, which I will not elaborate on. So we, in fact, recently wrote a proposal to the Indian Knowledge System Cell to be able to explore this and to see what the consecration process is. What is known as pran pratishtha and by mantras and chants. What does it really do to the structure? That's number one. That's a question. Second is, what does it actually do to us? How come we are subjectively, each one is affected? Can we study that objectively by using FNIRS or EEGs? And this is something that we are actually exploring at the Indian Knowledge System Centers for Mental Health Applications at IIT Mandi. So, this kind of interest led me to IIT Mandi. IIT Mandi have a collaborator, where the collaboration still continues. There, when I was talking to the director and a few other people at the Indian Knowledge Systems for Mental Health Applications Center, and because of my connection with yoga and with music and with Ayurveda and other forms of Indian systems that I have found personally work for me. So I was invited to teach a class on music or on Sanskritam, etc., which I declined, saying that rather than me teaching, I'll bring in the experts from around the world who will do this well for you. So I brought Chitravina Ravikiran to do a course on music and musopathy. So he and I taught co-taught a course in August. I thought 20-30 students will sign up, August of 2023, but 230 students signed up, and I haven't spent so much time grading for a single class, 3 assignments, and it was a lot of work, but it was a lot of fun. So that is the kind of interest that students in a technological institution have for Indian arts and Indian systems. Now, so since then, because of the interest, we actually formally, through the Senate, got approved a master's and PhD program in musicopathy and music, where we are actually looking into applying or various scientific methods in electrical engineering and bioengineering and psychology, in materials, various aspects of this, to understand different effects of sound on well-being. Music therapy is a field that has been around. If you hear this raga, this is found. If you hear Mozart, this is found. This has been published for a long time. But then the question always remains, what if you hear some music from an unknown culture? Will you have the same kind of effect? Or what is the difference? What is the contribution of cultural conditioning versus actual sound itself? The sound itself, energy is very small, so it has to be an effect that is it creates on the neurological system, which then is amplified and affects the overall health. So these are the things that we are looking at. Sonal Mansingh, Trichy Shankaran, and Professor Gautam Desiraju are advisors. Professor Gautam Desiraju, I must tell you, is one of the most highly cited Indian scientists who's living. I just met with him last month, and he took a liking to me, and he was teaching me a song of Dikshitar. So here is a short clip of actually, here is a short clip which I had recorded in anticipation of what Gopal said. I can sing for you, or you can hear this, or you can do both, whichever. Maybe I'll play this for a minute.
I think the voice is not clear. I'm not sure if
No,
Rohan?
voice is not coming. Yeah.
Yeah.
Okay, so the voice is not coming through?
Oh, sorry to interrupt, but we're coming close to the end of the session.
Okay.
So
But
can we
if-
start question and answers?
Yeah, Rohan, I think you can read out the questions. There's one by Sushant Jha. He's asked a couple of questions. Just 1 second. There's a question from Sushant Jha. He's asking, are you saying that the molecular thermal process can deoxidify oxidify the thermal reaction optimization process with the help of silica, carbon, and sulfur?
Okay, let me understand this question. You're talking about the molecular nano layer, what it can do at the interface, correct? Rohan, is that what you're asking?
Sushant.
Sushant, sorry. Is that what you're
Sushant,
asking?
if you are here, you can unmute yourself and ask
Yes.
Professor.
Okay, I see that he has
Professor
said
Ramanath.
yes. I see he has said yes. So yes, so the molecules at the interface, can change the interface properties quite dramatically. It can change the oxygen content. It can desiccate the interface. For example, if you use CF2 groups, you can make the interface hydrophobic, that is water repelling, which can change ionization and diffusion dynamics and kinetics. And we can actually do this quite precisely on surfaces. So I hope that answers your question.
Yeah. There's one more question by Mahendra Gattu. He's asking what is meant by yantra. And then he says our ancestors possibly used trial and error without fundamental understanding of material science. As you are a material scientist, you are possibly the best evaluator of early technological work in India before the European Renaissance. My question is, are you looking into any hypothesis in early Indian texts which can be investigated scientifically now?
Yes, the answer is yes. I mean, so yantra literally means a machine, okay, in Sanskritam. So yantra means something that does, so it has an effect. Now, it can be passive, it can be active. Right? Antenna is a yantra. It is, what does the antenna do? It is just there, but it does many things. It like picks up electromagnetic waves and so on and so forth. Now, in the context of well-being, we all have subjective experiences depending upon maybe belief, maybe like how attuned you are to certain thoughts and processes, perhaps. And I'm saying this without proving anything or without assuming anything, really. Now, we want to see what are the effects of this yantra when it is consecrated and not consecrated on different populations, to see if there is a difference at all. If there is a difference, then I think that's an important finding, that consecration actually is a process. How it works, we need to find out. Just because we do not know doesn't mean that it does not work. Second comment on this, our ancients, you're absolutely right. They probably had empirical knowledge. Much of it is empirical, but I think we cannot discount for other intuitive processes. Because as a material scientist, I must tell you, most of my novel ideas have come mainly from introspection, not by logic, really. Logic often can be a stumbling block to finding completely new ideas. I think Schrodinger is a good example. Schrodinger equation, we all know, has no proof, but it works. All right. So I think I would call it the Rishi effect, for lack of a better term. We need to understand what the Rishi effect is. I think it might have to combine advances in psychology, where we are dipping into the unconscious, collective unconscious. We are bringing out, into the conscious, because really all these are discoveries. These are all there. It's not inventions, so to speak. Did I answer your two questions, or did I miss any question here, Gopal?
Now, there's just one more comment by Sushant Jha. He says that Sir Ram Setu movie is inspired by material science. I don't know anything about the movie, so it must be.
Ramasetu. Okay, I haven't seen the movie. I don't watch movies much. Is it about Tamil, Hindi movie, or Tamil, or what is it?
You know, Sushant is there online. He can unmute
Sushant?
yourself, Sushant. I think they're forcibly muted everybody.
Okay. So I will check out the movie. I haven't watched the Ramasetu movie. Mahendra Gattu to everyone, sir. I'm reading. Okay. So I must say that I haven't watched the movie. I'll check it out. See, one thing that I find to be a privilege, I must say, is that coming from an ancient civilization, there's so much known, and so much that is unknown to us. Okay. And on the other hand, also given the privilege to explore in the unknown using the scientific method, I think more of us in different fields should pitch in and see, at least to show what works and what doesn't work. Because if something works, that is new. If something doesn't work, there's always the question of, have you devised the right experiment or not? It can drive further exploration.
Okay. And one more question that is there by Anmol. He says, Dear Professor, during the process of consecration, does the process happen at the prana level or does it also happen at the material level? Asking because Sadhguru has said that even if the Dhyanalinga stone wasn't there, the energy would still be present. I am not sure if this is a question relevant to the meeting today, Papia.
Yes,
Um,
certainly. Yeah,
I
so
can.
I will request, like, we are almost end part of the session. If you have any question, definitely you can reach out to us. And I will send a thank you note with YouTube video. You can go through one more time. And any questions, definitely I will send all that things to Professor Ganapati, and I will send his answer. consolidated answer to all the registered participants. Is it
Okay.
okay?
Papia,
Sorry again, Papia and Professor. I dropped off. Somehow I had an audio issue. So if you had questions that were not answered, definitely please do message us and we will follow up.
Okay.
So, Papia, if I may, I want to give a short answer to the question on the Pratishta. I will give a
Sure,
tangential answer, if you don't mind,
sure.
because I know for a fact that yantras work. It's my personal experience. Before that, if somebody had told me yantras work, I would not have believed them. I would not have disbelieved them either. Let me put it that way. But my driving force for looking at the consecration aspect is it is there. The science of consecration is very much there in our civilization. It is there currently also. But even the ones who consecrate it, there's very few, and they know the processes by which consecration happens. Okay. Now the thing about if it is material or non-material. Let me just share an experience, if you don't mind. So when you have this antenna kind of thing, the proximity actually matters. Beyond a particular point, you don't see the effect. Okay, this is all our, just like the Wi-Fi signal. But after repeated exposures to it, one thing that changed, for example, automatically changes is your breathing. And this is my personal experience. But this could be just a one-off thing. So this doesn't prove anything or disprove anything. Doing this collectively and studying this to see physically and non-physically distance and with time, and all these are studies, I think, that are warranted, should be approached with an open mind, with the idea that we should be able to accept if it doesn't work also.
Okay. Ramnath, now popular request for you to just sing for a couple of minutes. You can choose the genre, popular music or Carnatic, and then we'll just have a vote of thanks by the IITMAA, and then we'll conclude the session.
Okay,
Gopal, I
so
think that's the most amazing way to end this session.
Yeah.
So please, Professor, the stage is all yours.
okay, thank you very much. Since you did not hear that song properly, I'll sing the same song since audio was not heard. भारत देश हिताय भरतादि महामति सेवित भारत देश हिताय भरतादि महामति सेवित भारत देश हिताय कुरु सेवाम कुरु सेवाम कुरु सेवाम कुरु सेवाम आसेतु हिमाचल वन गिरिजन संरक्षणाय आसेतु हिमाचल वन गिरिजन संरक्षणाय वन गिरिजन संरक्षणाय वन गिरिजन संरक्षणाय कुरु सेवाम आयुरारोग्य विवर्धनाय धर्म संस्थापनाय क्षोभ निवारणाय सुभिक्षा परिप्रापणाय क्षोभा निवारणाय सुभिक्षा परिप्रापणाय दीनजन उद्धारणाय दीनजन उद्धारणाय कुरु सेवां भारत देश हिताय आनंदम ददानम दम ददानम दम ददा नम दम ददानम 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 दम ददा num dum da da 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 num dum da da.
Very, very good. And so many people have wished you, saying that it's beautiful rendition, melodious, so on and so forth. Thank you very much. Thank you very much, Ramnath. We all really enjoyed very, very thought-provoking and information session. And I could just observe that you have made some very important discoveries, and also that's just altering the landscape of your particular field of study. Okay, thank you very much for giving us time today. Can I just call somebody from the IITMAA to just propose a vote of thanks?
Yeah,
Yes,
thank
so
you. Yes.
definitely. Before Papia speaks,
Yeah.
I would like
Thank
to
you, Professor.
request Papia to give the vote of thanks. And
Yeah,
thank you,
thank you,
Professor. Thank you,
Professor.
Gopal. And we really appreciated this session. Papia, please
Thanks
go
to
ahead.
everyone for joining this session. So I hope you enjoyed the session. It's really definitely mixed of science and music and knowledge also about the, like all that our heritage. Thank you, Professor. It's really a mixology of everything. I'm sure everyone liked that, and I'm telling everyone if you have by tomorrow or day after tomorrow, I will send the YouTube link to everyone. You can go through once. If you have any questions that you missed today, you can write to us. We'll send that questions to Professor, and I will collect the answer from him, and I will get back to you with the answer. Thanks, everyone,
Thank you,
Thank you.
for
Papia.
your time. Yeah, thank
One
you.
last thing that I want to mention is that IITMAA is hosting Sangam in Bangalore on 4th and 5th July. 5th July is the most important date where our conference is happening. Please check out www.iitmaasangam.com and register if you haven't already.
Thank you very much for the opportunity,
Yeah,
Papaya,
thank you.
IITMAA, and Gopal, and
Yeah,
everyone.
and yeah, everyone. Thanks for joining the session. Thank you,
Thank you.
Gopal sir, for hosting the session.
Thank you.
Thank you,
Thank
sir.
you, everybody. Thank you.
Good night to everyone.